Check it out now, y'all.
nanoHUB-U, online instruction.
Hi again, welcome back. This is the fourth lecture in week 4, and we're going to discuss how to process the force curves that you obtain when you do a force versus displacement experiment in an atomic force microscope. First, let me say that I appreciate all the comments we're receiving on this through this online discussion forum. It's very helpful when you ask questions because we have a better sense of whether the information we're trying to transmit is getting through. So please keep up to date with that. Keep sending us questions. We'll do our best to get answers back to you in a short period of time. This lecture is really intended to walk you through a number of very simple examples. Basically, the issue is once your AFM has acquired a force versus z-displacement curve, what do you do next? How do you process that information? So let me first again show this standard picture that defines the coordinate system that we're going to use. This describes the basic force versus z-displacement experiment. Once again, you control z, your AFM adjusts z in a systematic way. As you approach the substrate to the tip, these tip surface interactions start to take place. These tip surface interactions cause the cantilever to deflect. The positive deflection, pos-q, is indicated in this diagram. And the interesting interaction forces are, of course, a function of this parameter d. So it's always important to be able to go from d to z, and the way to do that is by measuring q. So that's the fundamental point of the force versus z-displacement experiment. The other important parameter that you always have to keep track of is this interatomic spacing parameter A0, that's indicated in the right-hand corner of this chart. That parameter is not terribly well defined for any given experiment. Typically, it's on the order of 0.3 of a nanometer or so. That's typically the separation between atoms and solids. And so we'll be using that parameter in order to understand the experimental data that comes out of these experiments. So what I like to do is I like to run through about 2 or 3 real simple examples, show you how to think your way through, how to calibrate the data that comes out of the microscope. Like to talk a little bit about artifacts, problems that you may run into when you do these experiments. A lot of you will say, well, you know, my AFM system has software that allows me to just take the data curve and click on a few places, and then the software processes the raw data, turns it into useful information. My response is, yeah, that's great, that's wonderful, but the more you know about what you're doing, the better you're going to understand your experimental data. So it's kind of worthwhile to go through some simple examples, make sure we're all on the same page about how to process that data. So the way I like to lay this out is I have a standard slide, and in that slide there are 6 panels. And basically, we're going to start in the upper left panel, and we're going to work our way sequentially through each panel. Each panel requires a logical step that you have to take in order to get from one panel to the next. So first panel just shows the standard experiment and defines the coordinate system. It's important that you have those definitions in mind. The second panel at the top shows the typical data that you'll get out of a force versus displacement curve from your atomic force microscope. This can be considered the raw experimental data. The axes that are plotted may not be very meaningful, right? Because the y-axis is often the voltage from the photosensitive or the photo diode, and that voltage is in volts. It's not in newtons or nanonewtons, which is the force. So we have to go from that voltage versus Z, right? We have to go to in a systematic way to a plot that tells us the interaction force is a function of the gap separation D. So very often when you get raw data, the raw data could be floating in space. I say floating in space because there's no Z equals 0 associated with that data. The data could be offset from 0 volts, right? The offset is just a function of how carefully you aligned your photodiode, the laser spot on your photodiode before you actually took the experimental data. So the first step is you have to basically go in and define a Z equals 0 point. You also have to subtract off that DC offset that occurs when a tip is far from the substrate. The polarity of Z could be positive or negative. It just depends on the software system that you're using when you acquire the data, right? So I like to always think about Z as positive going to the right. So there may be a shift in Z that has to be achieved in the process of analyzing the data. Once your data has been zeroed and centered, as is indicated in the third panel on the top right-hand side of this slide, then the question is, how do you convert the voltage from the photosensitive detector, the voltage from the position-sensitive detector, how you convert that voltage into a displacement of the cantilever. And the way that's done is by you measuring the sensitivity of the optical system as it was when you took that data, right? So the optical sensitivity can change from day to day simply because it depends on how the laser is positioned on the cantilever, and it depends on the orientation of the cantilever as it's mounted into the AFM. So slight changes in orientation of the cantilever could in principle change the sensitivity. In this particular example, we're pretending that we are pushing on an infinitely hard material with an infinitely hard tip, so there's no indentation, right? That's not allowed. And also there are no surface forces, and of course you can tell there's no surface forces because the voltage from the position-sensitive diode, that voltage is essentially 0 as a function of Z as the tip approaches closer to the substrate. So what you have to realize is that you have to go through this process that I indicate in the fourth panel on this slide, right? During contact for an infinitely hard sample, the cantilever is going to deflect by exactly the amount that the tip sample, the cantilever is going to deflect by precisely the amount that the substrate is moved as it loads up against the tip. So this basically means that you want to convert the slope of the voltage versus Z curve. You want to convert that into a Q versus Z calibration. And the slope of the Q versus Z calibration is going to essentially be 1, which indicates that Z is equal to Q, right? So again, the logic is, since the sample and the tip are infinitely hard, no deformation occurs. If no deformation occurs, then as you decrease Z such that the substrate pushes against the tip, then ultimately the displacement of the cantilever is going to be precisely equal to Z. What that means is, that when the curve is properly calibrated, the slope when you're in contact is just equal to -1, and I indicate that in the fifth panel on this slide. So the mathematics required to achieve that is indicated in the fourth panel. It basically means that you have to determine the sensitivity parameter S, which is just equal to 1 over the slope that you measured in the third panel of the slide. So once you've got a curve which lists the cantilever displacement versus Z, then you can turn that into a force versus gap separation curve, simply because if you know Z and you know Q, then you know D, right? So you have to add Z to Q in order to get D, and the ultimate force versus distance curve, force versus separation curve that you would achieve from this experimental data, that's shown in the sixth panel on this slide. And basically what it shows is it shows that the interaction force is 0 all the way up to this arbitrary parameter A0, which is again on the order of 0.3 nanometers. Once the tip and the substrate are separated by this distance A0, then as you continue to load the substrate against the tip, all that happens is there's a hard wall interaction force that goes vertically upwards, okay? And that just follows because essentially Q is equal to Z on this infinitely hard sample, and so when you subtract, or when you add Q to Z with the appropriate sign conventions, you'll end up with the force curve that I've got drawn. So this is just one example, okay? Case one, I call it. It's the simplest one to think through. But the process for all the other examples that I'm going to list are going to be very similar to this. And so if you understand this one, I hope it's easy to quickly follow through on the other examples. So the second case, let's again consider an infinitely hard sample and tip. Let's say for some reason there's a long-range repulsive surface force, right? If there's a long-range repulsive surface force, right, then your output of the position-sensitive detector is going to vary as Z is systematically decreased. It's going to vary in a way that I indicate in the middle panel of the top of this slide. Ultimately, when your tip comes into contact with your sample, you're going to start to see a linear increase in the output from the position-sensitive detector with respect to Z, and I try to indicate that by the dashed line, right? So eventually, the output voltage of the position-sensitive detector will follow a linear dependence on Z. Again, the data may be floating in space, right? It may not be zeroed properly. There may be an offset in the voltage from the position-sensitive detector simply because you didn't spend enough time to center the laser spot in the middle of those four quadrants. But you can subtract all that off, and eventually you can end up with a plot as shown in the third panel, right? Now we've got everything oriented properly. We can see that the voltage from the position-sensitive diode is from the position-sensitive detector. We can see that voltage is 0 when the tip is far from the substrate. That indicates the absence of a surface force. But as you start to approach the substrate to the tip, you can see that the voltage from the position-sensitive detector starts to increase. That increase occurs when the tip is far from the sample, right, indicating the presence of a long-range force. So this is a toy model, but you can see how it captures some interesting physics. Again, you have to convert the voltage into a deflection, right, of the cantilever. The way that's done is by measuring the slope of the curve in the third panel, and then forming this sensitivity parameter S, which is essentially 1 over that slope. When you multiply the voltage by S, then you'll find that when you're in the contact region of the force versus displacement curve, you'll find that the slope of Q versus Z is -1, which basically means Q is equal to Z. And again, that's an indication that the tip is not indenting into the sample. As you displace Z, Q changes appropriately, right? So now that you've got Q and Z, you can always calculate D because D is the sum of Z and Q. That's indicated in the sixth panel of this slide. And when you convert the deflection of the cantilever into a force, you do that by simply multiplying by the known spring constant. Then you end up with the force versus gap or force versus separation curve that has some physical significance, and that's shown in the sixth panel, right? Again, the parameter A0 is completely adjustable. It's a number that you can set. Very often, A0 is set to 0, which basically means that the curve is shifted a little bit to the left. Those are just personal preferences. Different groups and different manuscripts have different conventions that they follow. So you just have to understand the convention that's being used and sort your way through it. I give an example of my third case that I'd like to consider is now a soft substrate, soft sample. Again, I'm going to consider the case of no surface forces. The new twist that comes into this discussion is that now the tip can actually indent into the substrate. That indentation is specified by this parameter minus d in the first panel of the curve. What you'll find is that the voltage from the position-sensitive detector again may have to be zeroed and centered. So that takes you from the raw data in the second panel of this slide to a shifted offset corrected data plot in the third panel. It's often very useful to understand that when you're pushing on a soft sample with the tip, this indentation occurs. That just simply means that your voltage from the position-sensitive detector, right, that voltage is always going to be less than what you would get if the sample were very hard, right? So the typical curve for a very hard sample, I've indicated that in red by the dashed line. Usually that's obtained by inserting a very hard sample into the AFM, doing a displacement versus force curve, force versus displacement curve, right? That allows you to measure the slope m. That slope m then allows you to convert, to calculate the sensitivity of your optical system, right? That sensitivity S then has to be multiplied by the voltage, and that gives you the result that's plotted in the fifth panel of this slide. The difference between the dashed red line and the actual experimental data, that's now the deformation that occurs, right? And you can actually measure that deformation as a function of z, and you can then convert the fifth panel to the sixth panel because now you know both q and z. So you can add q to z to get d. You can multiply the parameter q by k to get the force, and at the end of the day, you'll end up with a plot that looks something like what I've got in the sixth panel of this slide. What we've done here is we've made a distinction between a non-contact regime and a contact regime. When you're in the contact regime for a soft sample, of course, you're basically plotting the deformation of the sample versus d, right? And not the tip sample gap. Tip sample gap is basically fixed. It's fixed at A0, right? You can't push the tip any closer to the substrate than this parameter A0. But if the tip indents into the substrate, then you can display that on this plot, and that's actually what's done here. So that's a real quick overview of how you have to think your way through these experimental data for different situations. It becomes very helpful if you have a simulation tool to help go through all this arithmetic so you don't have to think it through every time. And of course, that's what VEDA is going to offer, right? Well, in the fifth week of this part one of this course, we'll talk about VEDA simulations of these parameters where you don't have to worry about all these details, but you can just click on buttons and actually get accurate numerical simulations in a matter of seconds. I'd just like to say that the calibration on a hard sample usually is done after the indentation on a softer sample. It's important for you to do that calibration because that defines the limiting case where there's no indentation. That limiting case changes from day to day, right? It depends on how the laser beam is adjusted onto the cantilever. It depends on a variety of things, right? It depends on the speed of the indentation, so that's the piezo displacement. It depends on whether you're doing that slow or fast, so the calibration could vary slightly with that parameter. The calibration could also depend on the amount of cantilever deflection. So it depends if you're indenting just a little bit or a lot. That'll also change the calibration. So there's also nonlinearities in the Z-piezo that you might have to take into account, and possibility of piezo aging. So the sensitivity that you might get today could be slightly different than the one you're going to get a week from now, simply because your Z-piezo may have changed. So there's a lot of reasons why you constantly have to repeat these indentation curves on hard samples. And it's important when you do those calibrations on hard samples that you use exactly the same parameters, exactly the same laser alignment that you used when you took the data on a softer sample. Ultimately, the goal is, when you're doing indentation on softer samples, the goal is to measure the indentation or the deformation of the tip into the sample. And so here I just run through an example of that, showing you that it's kind of a two-step process. That's the way I like to think about it. I like to think about first putting the tip on an infinitely hard sample, finding out what the force would be required for a particular value of Z. That's indicated by 0.1 in this slide. And then I like to, at least conceptually, turn on or turn off the hardness of the sample, let the sample assume whatever elastic modulus it might have. And when you do that, of course, the tip will then indent into the sample, so you'll go from 0.1 to 0.2. And the difference between those two curves is then just the deformation that occurs. The deformation is a function of applied force, is something that's of fundamental interest. So what you can do is you can take that deformation, plot it as a function of applied force, and then you can then use your best theory to try to explain the observations that you've actually measured, right? So this is just a typical example of trying to fit some theoretical approximation to deformation data that was achieved by experimental data. There are many examples. Here I just show how one of the students here at Purdue has converted cantilever deflection versus Z-displacement. That's shown on the left region of the curve. How you convert that into a force versus separation or a force versus gap plot, which is more interesting, more meaningful. You can see there's a lot of noise in going from the curve on the left to the curve on the right. The noise just comes about because, right, you're doing this conversion between Z and D, and that means you basically have to add Q to Z. And if Z and Q are not known accurately, then your estimate of D is going to be a little bit noisy, and you can see that in the wiggle and the wobble of the data. But ultimately, this is the goal, right? To go from the curve on the left to the curve on the right. When you do this, there are many artifacts that you potentially could find, and I just wanted to real quick step through those artifacts just to give you some sense of what you have to do, and if you see something that doesn't look right. So we've already talked about the offset problem. You clearly have to subtract that offset from your experimental data. The offset is usually just a just caused by the fact that you didn't carefully align the laser beam on the position-sensitive detector at the beginning of the experiment. Sometimes if you do an approach curve that spans a huge range in Z, right, you'll see these oscillations or these wiggles in the curve. That's usually an indication that the laser spot is not accurately aligned on the cantilever, but that actually some of the laser light is being reflected from the substrate into the position-sensitive detector. You're getting some weird interference, right? So that basically means you have to reposition the laser spot on a cantilever, possibly use a slightly wider cantilever if you happen to see something like this, right? Very often you'll see a very hysteretic force versus distance curve. So you see an approach and a retract or a retrace curve that don't match at all. Usually that means there's some sort of a hysteretic behavior in your Z piezo. Maybe you have to warm the piezo up a little bit. So maybe you have to do some force versus distance curves when the tip doesn't even come into contact with the substrate. Once things warm up, this effect should go away. If you see a large offset between the approach and the retract curve, right, that could mean that you're trying to do the force versus distance curve too rapidly, right? So slow it down a little bit. And that should get rid of this problem. And then lastly, if you see a really open loop hysteresis in the contact region of your sample, right, so that the approach and the retract or retrace curve are completely different, it probably means you're indenting way too much. You're inducing a plastic deformation in either your tip or your substrate as you indent. So don't reduce the applied force, right? Reduce Q, and this effect may go away. So all these force versus displacement curves, these can be simulated accurately in VEDA. We'll talk about that in week 5 of the class. VEDA then allows you to get a large number of different outputs, which are very helpful in trying to understand some of the basics behind this very simple experiment. But it's very powerful because it tells you something fundamental about how the tip is interacting with the substrate. So we'll talk a little bit more about this in week 5. This is more of a preview of what's coming, and I'll just end, sorry I ran over a couple minutes on this lecture, but I'll just end up by saying that the next lecture we're going to discuss how to do modulus and adhesion maps by basically doing force versus displacement data curves at different points on a sample. And this will then allow us to map out in a systematic way if the modulus of the sample varies with position, and also whether the adhesion of the tip to the substrate varies with position. So we'll discuss that in the next lecture. Thank you very much.